For assignment 28, number 7, first off, I labeled this is R3 and this is R4, which helps me for later. So the first rule of op-amps is that there's no current that can go into an op-amp, and so that means that the current through R1 is the same as the current through R2, and the current through R3 is the same as the current through R4. So I calculated those currents using V equals IR. So through R2, it's V minus V out over R2, and for R1, it's V1 minus V minus over R1. And so because these are equal, you can set them equal to each other, and I solved for V minus. So I had V1 over R1 plus V out over R2, all times R1, R2 over R1 plus R2 is equal to V minus. So then I went to the next ones and solved for, so through R3 it's negative V2 plus V plus over R3, and for R4 it's negative V plus over R4. Set those equal to each other, and so I solved for V plus, so I got V plus is equal to V2 over R3 times R3 R4 over R3 plus R4. So then I went and used the second rule of op-amps, which is the difference between the two. The V plus and V minus has to be 0. So I replaced all of my R3s with R1s and R4s with R2s so that I could put them together. And then I found the difference between them and solved for V out, and I ended up getting V2 minus V1 over R2 times R2 over R1 is equal to V out. For assignment 28, number 8, for part B, I corrected my answer to say that IB has to be between 0 and approximately 25 microamps. This is because at 25 microamps, the transistor is no longer in saturation. Where the load line crosses the curve of the transistor's current, the transistor will no longer be in saturation at this intersection. And then for part E, if VCC is halved instead of doubled, it's going to decrease. This is because if VCC were halved, the load line moves to the left, causing intersection between the load line and the curve to be in the curved part of the curve rather than when it's in saturation, thus causing IC to decrease.